Hi everyone, let's start chapter 9 today. So do you remember what we went over last chapter? We talked about series, but those are series with numbers, right? And in this chapter, we actually will talk about series with variables, x. Alright, so 9.1, approximating functions with polynomials. Big idea. Series involving a variable raised to a power are called power series. They're extremely useful as an alternative way to represent any function, since their computation involves only addition, subtractions, and multiplication. We can use the sum of the first n terms of this series. So this is a polynomial, okay? The first n terms of a series is a polynomial. We can use this polynomial to approximate any function. Big skills. You should be able to compute the Taylor polynomials to approximate a given function. Alright, so let's first look at the definition. What is a power series? If z0, z1, z2 are constants and x is a variable, then a series of the form sum of ck x to the k is called a power series in x. And all those ci, c1, z2, c3, all those we call the coefficients. So those are coefficients of x. So you can see we have the powers of x. And the series of the form c0 plus c1 x minus x0 plus c2 x minus x0 squared. So this is called power series in x minus x0 because you can see this series contains powers of x minus x0. And x0 is called the center of the series. And this type of the series is called power series because it consists of the powers of x or x minus x0. So let's look at some example of the power series. The easiest one, x to the k. So look at our index, our k start from 0. So when we try to plug in 0, we get x to the 0 as 1. And here, keep in mind that 0 to the 0 is defined to be 1. And 0 factorial is defined to be 1. Okay, so when you plug in the first term, you see x to the 0, that's 1. And the second term, you plug in k equals to 1, so you have x to the 1. And the third term, you plug in k equals to 2, so you have x squared. Okay? And the next examples, we have this formula. So we plug in k equals to 0. So minus 1 to the 0, 0, x to 0 is 1. Sorry, I say something wrong. Minus 1 to the 0 is 1. And x to the 0 is 1. So 2k becomes 0. 0 factorial is defined to be 1. So the first term of this sequence is 1. And the second term, you can plug in k equals to 1. So that's why we get negative x to the 2 over 2 factorial. Okay, and next, when we plug in k equals to 2, minus 1 squared becomes plus 1. And then we have x to the 4. 2 times 2 is 4 over 4 factorial. Okay, everybody? How about the next one? So the next one, this is our formula. We plug in k equals to 0. Then the first term is 1. And when we plug in k equals to 1, we get x minus 1, right? So actually, these guys, they are power series in x. And this guy, this is actually a power series in x minus 1. So what's the center for a power series in x? The center is 0, because you can think about x as like x minus 0. So center is 0. How about the power series in the x minus 1? What's the center? Yeah, the center is 1. Okay? So those are the examples. So suppose f is any function that's differentiable on an interval I containing the point A. Well, do you remember in Calculus 1, we talk about the linear approximation. So linear approximation tells us that we can use the tangent line at that point. So you can see here, the pink line is the tangent line at that point A. We can use the tangent line to approximate the function value when x is near A. Okay, for example, if x is here, you can see this guy and this guy. This guy is L of x, and that guy is f of x. You can see L of x is very close to f of x. So far, so good, everybody. And what is the tangent line equation? Well, we use the point slope form, right? We need a point on the line and a slope. Well, the slope is the derivative evaluated at point A, right? So that's why point slope form, we have y minus f of a, the y coordinate of that point, equals to the slope, the derivative at a, x minus a. So that's why you both sides add f of a, so you get, this is a tangent line equation. Okay, so this is a tangent line equation. It's also the linear approximation. So today we're going to talk about like a higher degree approximation. How about the quadratic? So the quadratic approximation, we have 3 terms instead of 2 terms. So we have f of a and f prime of a times x minus a. So this is like what we had before, but we have an extra term. So this extra term is the second derivative over 2 times x minus a squared. So I will explain later why we have this term. Okay, so this extra term is designed such that the P2 of x, when we plug in a, it equals to f of a. And the P2, when we differentiate and we plug in a, well, that will equals to f prime of a. And the second derivative, when we plug in a, is going to be the second derivative of a. Let's see whether this is true. Okay, so this term, we design this term so that it will satisfy. So we design so it satisfy all of these 3 conditions, okay, or 3 equations. So let's check it. Okay. All right, so this is P of x, right? So when we plug in a, we see, oh, x minus a is gone, x minus a is gone. So that's why we have P2 of a equals to f of a. So this one, we have that. How about the second one? What's P2 of x? Well, P2 of x, this is constant term. The derivative of constant term is 0. And this term is a linear term. The derivative of x is 1. So we get f prime of a. And this term, you see, x squared derivative is 2. So that is f prime prime a. This is the constant multiple times 2 times chain rule x minus a times u prime. But u prime is like x minus a prime, which is 1. So you can see the 2 cancel. We have f prime a plus f prime prime a times x minus a. So now when you plug in a, we get what? We get f prime of a, and then this guy, when you plug in a, x minus a is 0. Right? So that's why we have the second one. How about the third one? We take one more derivative. Well, derivative of f prime of a is 0, and then the derivative of this guy is f prime prime a constant multiple. Derivative of x is 1. So that's why we have this guy. So that's why when we plug in a, we also have this one. Okay, so when we plug in a, we get P2 of A is F prime prime of A, which is this one. Okay, so that's why you see the pattern. The pattern here, we have the zero derivative, that's the function f. Here we have the first derivative, and then we have the second derivative. So second derivative, and here we have an extra 2. Okay, why we have a 2? Well, if you can remember in the process of computing the derivative, the 2 actually help us to cancel out with the 2 here. Okay, so that we have f prime prime of A. Okay, so that's why the new term is the second derivative over 2, and because it's quadratic, so we have the quadratic factor x minus a squared. So this is the quadratic approximation. So far, so good, everybody? Alright, so let's look at example 1. Part A, find the linear approximation for f of x equals to ln of x at x equals to 1. Okay, let me use my... Okay, so that's part A. So f of x equals to ln of x, and my A is like 1, right? Because we're looking for the linear approximation at x equals to 1. So 1 is like our A. Then what is f of A? Well, ln of 1 is 0. And then we also need to take the derivative. The derivative of ln of x is 1 over x. So f prime of A is 1 over A. A is 1, so we get 1. The slope is 1. So what is the linear approximation? So P1x is f of A plus f prime of A times x minus A. And my A is 1. So f of 1 is 0. F prime of A is 1. And then we have x minus A. A is 1. So the answer is x minus 1. That is the linear approximation. Okay. Part B, what is the quadratic approximation? Well, quadratic approximation is like the linear approximation plus an extra term. For the extra term, we need the second derivative. Well, the second derivative is the derivative of 1 over x. Well, that is minus 1 over x squared. Do you guys all get it? Yes? So, and then we need to plug in f prime prime A. So that is, we plug in 1 in it, so 1 over 1 squared. Well, that's minus 1. So this is minus 1. This is second derivative of f when we plug in A. Alright, so what's P2? So P2 is like P1, so what we had before, plus the extra term. The extra term is second derivative over 2 times x minus a squared. Okay, keep this in mind. And then P1 of x is x minus 1 plus second derivative, which is negative 1 over 2, and then x minus 1 squared. So let's rewrite it. And this is minus 1/2 x minus 1 squared. Okay, so keep it like this. Don't expand it. Just keep it like this. Okay, this is great. And this is our quadratic approximation. So far, so good, everybody? So part C. Use this approximation to estimate the value of ln of 1.05. Okay, so the main goal of using this approximation is, suppose we don't have a fancy calculator. Okay, so we have a calculator, but it's very basic. We can only do 4 operations: the plus, the minus, multiply, and divide. So only 4 basic operations we can do. Okay, so ln of 1.05. Wow, how can we calculate that? Well, you can use this linear approximation and the quadratic approximation, because ln of 1.05 is like it's like f when you plug in x is 1.05, right? If we use the linear approximation, then it's approximated by p1 of 1.05, right? So what's p1 of 1.05? Well, p1 is x minus 1. So p1 of 1.05 is 1.05 minus 1, which is 0.05. So far, so good, everybody? How about we use the quadratic approximation? Well, then that is p2 of 1.05. p2 of 1.05 is 1.05 minus 1 minus 1 half, 1.05 minus 1 squared. Okay, now what happened? Well, this is 0.05, and then we use it to subtract. Well, that's 0.05 squared. See, here we have subtraction and multiplication, so we are able to get the answer by hand, but you're allowed to use your calculator. But you can only use the four basic operation: multiply, divide, add, and subtract. So 0.05 minus 1/2 times 0.05 squared. So the answer equals to 0.04875. Okay, so let's check our work. You know, the good thing about this problem is we can always check our work. Okay, so check our work. ln of 1.05. Now plug in your calculator. What do we get? So ln, so I hope everybody you can put it in with me. 1.05. My answer is 0.048790164. Are they close? Are they close? Yes. So they're close, and you can see the quadratic approximation is closer than the linear approximation. And that makes sense because you have your function looks like that, right? One is right here. Okay, so if you use tangent line might look like this. But if you use your quadratic approximation, quadratic is like a quadratic polynomial, so it is like that. Okay, quadratic polynomial. You can see, let's say if we look at this point. See, if we look at this point, you can see the quadratic one is closer than the actual value than the linear one. Okay, so actually when we increase the power of the approximation, we will get closer and closer approximation. So far, so good, everybody? Okay, so let's continue. So in general, not only quadratic approximation, we can have higher order approximation. So let me introduce the Taylor polynomial. So the Taylor polynomial, let f be a function with f prime, f double prime, and the f derivative defined at a. Then the nth order Taylor polynomial for f with the center at a, denoted by p sub n, has the property that it matches f in the value, in the slope. So the value is like f of a equals p of a. So it means the first derivative. And all the derivatives up to the nth derivative at a. So that's why we have they match for value and they match at the first derivative, they match at the second derivative up to the nth derivative. Okay, so let's look at the formula. Well, see, f of a, that's what we've seen before. F prime of a, x minus a, that's what we have seen before. F prime of a over 2 factorial, this is like what we have seen before. So actually, what happens is you're gonna have the last term, you're gonna have the nth derivative over n factorial times x minus a to the n. Okay, so all the smaller ones also satisfy those rules, Well, you just let n goes from 0 to n. Okay, so you just need to remember this formula, and then plus the lower terms. We can deduce from that. Okay, so last time we see why we have a 2. We have a 2 because when you differentiated this guy, we have 2x minus a, so that 2 can cancel with that. And so the n factorial actually taking care of that. Because if we look at the nth derivative, well, when you take the first derivative, let's do it here. So p n x prime. When you take the first derivative, the constant term f of a is gone. And then f prime of a, derivative of x, is 1. And then next, we have the second derivative over 2. Derivative of x minus a squared is 2x minus a, right? And we have the higher term. And then the last term, we get f sub n of a over n factorial. And when we differentiate, we get n times x minus a to the n minus 1. So far, so good, everybody? You see, we can cancel the 2 right here. We can cancel the n. So we have n minus 1 factorial. Okay, so that's why when you plug in a, you can see all the terms with x minus a is gone. So that's why you only have p prime of a equals f of prime of a. And then you continue to take the second derivative. The first constant term is gone. And then this one, you get f prime prime a. And then derivative of x minus a is 1. And then plus the higher value, the higher terms. The last term is the nth derivative over a, and then n minus 1 factorial. But now, the derivative of x minus a to the n minus 1 is n minus 1 times x minus a to the n minus 2. You see? That n minus 1 cancel. We have n minus 2 factorial left. And with this patterns, it helps us to match all the derivatives. So that's why we have the n factorial at the bottom. Okay, so keep in mind, our formula is the nth derivative over n factorial times x minus a to the power of n. Okay? And here, that means the coefficients. The coefficients is the kth derivative over k factorial. So keep this in mind. So we're going to use this formula throughout the whole chapter. So this is so important. So I hope you can remember. So remember this formula just like remember your name, okay? So if you cannot remember it, tell me your phone number. I'm going to call you at the midnight and ask you, hey, wake up. What is the formula for the Taylor polynomial? Nth derivative over n factorial times x minus a to the power of n. Okay, so I really hope that you can close your eyes and read it one more time with me. Nth derivative over n factorial times x minus a to the power of n. Alright, so let's look at more examples. Example 2. Find the Taylor polynomials P1 to P7 centered at x0. X is 0 for f of x equals to sine of x. Alright, so we start with the first derivative. The derivative of sine x is cosine x. How about the second derivative? Well, the second derivative of cosine x, so that's the derivative of cosine x. So minus sine x. And then the third derivative of sine is cosine. So negative cosine x. And the fourth one, derivative of cosine is minus sine. So negative become positive. Oh, can you see? This is the same as what we started with. So it actually, after 4 derivative, it's just go back. It's like a periodic, right? Okay. So we know that the fifth derivative will be cosine x. The sixth derivative will be negative sine x. the 7th derivative will be negative cosine x. And the 8th one will be sine x. Okay, so let's summarize those patterns. So what's 5? So here 1 and the 5th derivative, that means 4k plus 1 derivative, where k is any integer. Okay, that is greater or equal to 0. And then this guy is like 4k plus 2. This is 4k plus 3. And this is, do we need 4k plus 4? No, we only need 4k. Alright. What happened when we plug in 0? Alright, when we plug in 0. So, I really hope that you can distinguish, because I do see many students say, oh, this is I plug in 0 and cosine 0 is 1. Okay? No, don't say they're equal. They're not equal. Okay? So this guy on the left, they're function of x. But when you plug in zeros, they are numbers. So they are not equal. So don't put they're equal. Okay? So here, let's plug in 0. We get cosine 0, which is 1. And then when we plug in 0, negative sine 0 is 0. And then when we plug in 0 in the negative cosine, we have minus 1. And plug in 0 for the sine, we have 0. Alright, everybody? Okay. So let's see. What's P1? P1 is f of a. So sine of 0, which is 0, plus f prime of a, which is 1, times x minus a. Okay, so the answer is x. That's P1. How about P2? Well, P2 is similar to what we had, plus a new term. A new term is the second derivative, plug in 0, which is 0 over 2 times x minus 0 squared. But because this guy is 0, so this guy is 0. So the answer is just like P1x. How about P3? Well, P3 is what we had before, but the extra term is the derivative over 3 factorial, and then x minus 0 to the cube. Well, what we had before is x. Okay, so that's P2 of x is x plus, the next term is negative 1 over 3 factorial x cubed. That's P3. How about P4? Then can you see that P4, because the fourth derivative is 0, so this is the same as P3. So that is x minus 1 over 3 factorial x cubed. How about P5? P5 is what we had before. Plus the fifth derivative. The fifth derivative is 1. So 1 over 5 factorial, and then x to the 5th. Okay, so that is P5. How about P6? So P6 is, because the sixth derivative is 0, so that's why will be the same as the fifth derivative. Okay, how about P7? Well, is whatever we had before, but the new term. What is the new term? The new term is minus 1 over 7 factorial x to the 7. So this is the P7. All right. So far, so good, everybody. And you can see we come up with a pattern. The derivatives repeats every 4 derivatives. It repeats. So that's why we write down P1 and P2 because the second derivative is 0. Second derivative is 0, so we get the P2 is the same as P1. And the P3, we have an extra term of the third derivative, which is -1 over 3 factorial times x minus a to the cube. Okay, and P4, because the fourth derivative is 0, we have P4 is the same as P3. And for P5, so for P5, we have the extra derivative because the fifth derivative is 1. So we have the extra term is 1 over 5 factorial times x to the fifth. And because the sixth derivative is 0, so that's why P6 is the same as P5. And for P7, the extra derivative is, because it's -1, so we have an extra term of -1 over 7 factorial times x to the 7. Okay, so that is example 2. Let's continue. Example 3, part A. Find the Taylor polynomial P1 up to P3, so P1, P2, P3, center at 0 for e to the x. Okay, so let's do the same thing. F of x is e to the x. What's f prime of x? Well, the derivative of e to the x is e to the x. How about the second derivative of e to the x? So you realize all the derivatives just stay the same. They're all e to the x. Right? Okay, so that's why when we plug in x is 0, we get f of 0 is 1, and f prime of 0 is 1, f double prime of 0 is also 1. So all the derivative when we plug in 0 is going to be 1. Okay, so what is P1? So P1 is f of 0 plus f prime of 0 times x minus a. A is 0. So that is 1 plus x. That is P1. So far, so good, everybody? And then what's P2? Well, P2 is what we had before, but the extra term, because the derivative is also 1, over 2 factorial is the same as 2 times x squared, right? And how about P3? That is what we had before, plus the extra term. Oops. What's the extra term? Because the derivative is 1 over 3 factorial. What's 3 factorial? 3 times 2 times 1, that is 6. Okay, so that is P3. So this is part A. Part B, use P3 to approximate e to the 0.1 and e to the minus 2.5. So you can see, look at this picture. I give you the picture here. So we have the exponential function. That is the pink line, right? And the P1, this picture use T because T also stands for Taylor polynomial. Okay? So P1 is a line, so which is the black line. And then P2 is parabola. So you can see the orange parabola, it's going up. And then P3 is the cubic curve, so it looks like that. Okay, so that's the blue line, and you can see the picture, the blue line is closer to the pink line, that's our original function, and then the orange line, and then the black line. Okay, so if we increase the power, the terms of the Taylor polynomials, we actually get a closer and closer approximation. Okay, let's continue. Look at part B. So part B, use P3 to approximate e to the 0.1. So e to the 0.1. This is f of what? x is 0.1. So a typical error is sometimes students plug in e to the 0.1 here. No! X is just x is just 0.1. Think about it. If you plug in e to the 0.1, that means you know how to calculate e to the 0.1. Then you don't need this Taylor polynomial approximation if you know how to calculate e to the 0.1. Okay? We use this Taylor approximation because we don't know how to compute e to the 0.1. We know how to add, subtract, multiply, and divide, but we don't know e. Okay? So that is f of 0.1. That approximately by P3 of 0.1. So 1 plus 0.1 plus 1/2 0.1 square plus 1 over 6 0.1 cube. Alright, so plug this in your calculator. What do you get? Okay, so plug this in your calculator. I get 1.10516 and the 6 repeated. Okay, so and let's check our work. So the good thing about problems in these sessions, we can always check our work and we know, we have an idea whether we're doing right or wrong. So plug in our calculator. So e to the 0.1. Okay, let me plug it in. So e to the 0.1, that is 1.105170918. Are they close? Yeah, quite close. Yes. So it means we're doing right. If you get the answer is quite different, maybe you get a mistake, so check your work in that case. Okay, and we need to compute e to the negative 0.25. So e to the negative 0.25, that is f of negative 0.25. Approximately by P3 of negative 0.25. So we plug in x is negative 0.25. Well, x squared, the negative squares become positive, so 0.25 squared. And then negative cube becomes still negative, and then 0.25 cube. So far, so good, everybody? So we plug this in our calculator and let's see, what do I get? 1 minus 0.25. So I hope all of you can plug it in with me, okay? Because sometimes learning how to plug your numbers in your calculators is also very important. Even though it looks like easy, but sometimes if you press the wrong button, it will actually screw up your number, right? So I get 0.778645833. Okay, let's check our work. The good thing is we can always check our work here. So e to the minus 0.25, put this in our calculator. What do we get? So e to the negative 0.25, we have 0.778800783. Are they close? And sort of, at least the first 3 decimal places are the same. Alright. So that is the Taylor approximation, okay? Taylor polynomial approximation. So I really hope that you can stop the video here and try to work on example 4 and example 5. Are you done? So let's check our work together. So here you can see the function is not given, so we're gonna define the function. So the first step, we define our function to be, I would say, square root of x, right? Okay, what is the a? Well, Here, our x is like 18. So a is a good number that is close to 18. What does a good number means? Well, a good number is a number you can calculate, so we can calculate f of a and f prime of a easily. Okay? So what is the good number? Okay, 16, right? We know square root of 16, so a is 16. So that's why f of a is square root of 16, which is 4. Okay, so take the polynomial of all the three. Okay, so second step, we're gonna keep taking the derivative. Well, the square root of x is like x to the 1/2. So when we take the square root, when we take the derivative, 1/2 stays. We have x to the minus 1/2. Okay, and what's f prime of a? A is 16. So we have 1/2. This means x stays in the denominator. So square root of x, so that's like 1/2. Square root of 16 is 4. So 1/2 times 4 is 8. Okay, we continue. Second derivative, we multiply by negative 1/2, so we get minus 1/4. X to the negative 3/2. Okay, what happened when we plug in 16? Minus 1/4. So this means x to the 3/2 stays in the denominator. Okay, what is that? 4 stay there. Square root of 16 is 4. And then we have a 4 cube. So this is the same as minus 1/4 to the 4th. So let's keep it like that. And we plug in the numbers at the end using our calculator. Okay, so we can use our calculator, but keep in mind, we can only use the 4 basic operation, plus, minus, multiplication, and division. Okay, so the third derivative is minus become plus, 3/8, x to the negative 5/2. And when we plug in 16, we get 3/8. This is like, sorry, I should plug in the 16 there, because when we plug in 16, those are numbers. Those are not a function of x. So 16 to the 5/2. Well, that's the same as that's the same as 4 to the 5th. Okay, so we have all of these. Now let's combine them. Okay, so let's put them together. So P3 of x is f of a plus f prime of a times x minus a plus f prime of a over 2 factorial times x minus a squared plus the triple derivative, we plug in 16, so 3/8, 4 to the 5th, over 3 factorial, so 3 times 2, and then x minus 16 cube. So this is what we get. So far, so good, everybody? Alright. Finally, square root of 18, that's approximately by that's the same as f of 18. So I want to emphasize what is x. X is 18. So that's P3 of 18. That is 4 plus 1/8 times 18 minus 16 is 2. And then we have minus, this is like 2 and 4 to the 4 downstairs. So 18 minus 16 is 2. So 2 squared. And the next term we have 8, 4 to 5th, 3, and 2. And then this is 2 cube. Okay, we can simplify some terms so we don't need to plug everything in there. Okay, so we can simplify here. We get 4 in the bottom. We can simplify here, so we have 4 cube. Here we can simplify the 3 and 2 cube is 8. Okay, so plug the rest into our calculator. Okay, so we have 4 plus 1 over 4 minus 1 over 8 plus 1 over, don't forget the parentheses, so 4 to the 5th times 2, close the parentheses. So my answer is, okay, it's approximately by 4.242675781. Okay, let's check our work. So if we plug in our calculator, and what's square root of 18? That is approximately by 4.242640687. Are they close? Yes, they're very close. So that is our approximation. Okay, everybody? So please work on part example 5. Are you done? Let's check our work together. So actually with the videos, we can actually go over more examples. So I really hope that you can, for all these examples, you can try it first and before we continue. Okay, so this is a good opportunity for you to learn. You can try it and then watch the solution. All right. So what's A? A is a good number such that you know the 5th root of that number. Well, let's see. I think I might make a mistake. Okay, I think this should be the 6th root. Let me change that. Okay, so because the 6th root, we know the 6th root of 64 is 2. So A is actually 64. Okay, then f of A is 7 over 6 roots of 64, which is 2. Okay? Alright, so let's continue. We're gonna do the first derivative. Well, this guy is 7 times x to the minus 1 over 6. So the derivative, we get minus 7 over 6. X to the, subtract 1 from it. So 7 over 6. So far, so good, everybody. And when we plug in A, what happened? So we get negative 7 over 6. This means that x to the 7 over 6 is in the denominator. So x to the 7th is 2. So we have 2 to the 7 in this case. Okay, how about the second derivative? We multiply by negative 7 over 6, so we get 49 over 6 times 6, 36. X to the, subtract 1 from it, so 13 over 6. Okay, so second derivative, when we plug in 64, 49 over 36. And 64, 6th root of that is 2, so 2 to the 13. Okay, and then the third derivative. Okay, the third derivative, we multiply by negative 13 over 6. Then we have 6 to the negative 18 over 6. Oh, sorry, 19 over 6. Okay, and the third derivative, so it's gonna be a big number, minus 49 times 13 over, let's put 6 cubed, okay? And then the denominator, so it's like 2 to the 19, okay? This is a big number. Let's see whether our calculator can calculate this big number. So, but the method or the process how we compute is very similar to what we have done, right? So that's f of a, f prime of a, which is negative 7/6, 2 to the 7, x minus 64. F prime prime of a, so 49, 36, 2 to the 13, x minus 64. And then we have minus 40, over 2. Don't forget, it's the second derivative over 2 factorial. And then here is the third derivative over 3 factorial, means divided by 6, extra 6. And then we have, that was square, x minus 64 to the cube. Okay, so next step, our functions is f of x is 65. Okay, we plug in it. So we have 7/2, and 65 minus 64 is 1. So minus 7/6, 2 to the 7, plus 49/36, 2 to the 13, times 2, and then minus 49, 13, 6. We can combine 6, so that's 6 to the 4th, 2 to the 19. Okay, let me see whether I can plug this in my calculator. Actually, yes, I can calculate in my calculator, and I got 3.4909675555. Yay! And how about, let's check it. So 7/6 roots of 65, we plug it in our calculator. What do we get? So 7/65 raised to the 1/6. Okay, so that equals 3.490967566. Wow, are they close? Yes, they're so close. Okay. So this is our answer of example 5. Okay, so we talk about any functions. We can always compute the Taylor polynomial and use the polynomial to approximate it. The good thing is we might not know how to calculate square roots, cube roots, natural log, or exponential functions, but we can use the polynomial to approximate it. So the basic operation we just need to do is like plus, minus, multiply, or divide. Okay, so it's good for some operation we don't know how to calculate, like natural log or exponential function. Okay, we can transform the problem into a polynomial. Polynomial we can compute. Okay, all right, bye.